The answer is to control the output voltage and the frequency, right? Output voltage and frequency for different applications. Sometimes we need to control the voltage of the inverter, or sometimes we need to control the current, right? Like application like the motor drives, so we need to control the output voltage and the frequency. In case of applications like the grid integration, so we need to control the in other words, we will operate the inverter as a controlled current source, so that inside that, so we'll control inside current, so we need to control either by maintaining the DC link voltage constant or the allow the DC link to vary, right? So in case of drives, so mostly we will operate in a voltage control mode. So as we discussed, there are so many PWM methods are there, so especially for the multi-level inverters. So all these methods are based on whatever the method discussed for the two-level inverters. So these are the natural extensions of two-level inverters. So as any methods, like any PWM techniques, there are two methods are there. So one is the space vector based methods, or the vector based algorithms, and the voltage level based algorithms. So the difference is that in case of vector based algorithms, so the entire three phases are controlled together, right? So all three phases are treated as one unit in case of vector based methods like space vector modulation and all. So whereas this method, so voltage generate or the voltage level based algorithms, so will control the individual phases, so A phase, B phase, C phase separately. So these are the difference. But in case of vector based methods, so all three phases are controlled together, right? So in case of space vector based algorithms, that is one is the space vector modulation and the space vector control. So both are more or less similar only. There are different algorithms are there, like 2D algorithms and 3D algorithms. So these 2D and 3D algorithms, the basic difference is you have extra access, for example 3 level or 4 level, or in case of multi-phase converters we normally go for the 3D based algorithms, right? So here the space vector based are complex when compared to two level inverters. So why it is complex means you have a lot of switching. In case of two level inverter we have 8 switching states, right? So out of 6 are active switching states, and 0 or 2 are the zero switching states. So likewise if you go for 3 level, so we have 3 phase, so 3 to the power of 3, so that is 27 switching states will be there. Again out of the 27, 3 will be 0 states. Like it is 5 level, it is 3 to the power of 5, 125 switching states. So from that switching states, like we have small vectors will be there, medium vectors, large vector will be there, and the full vectors will be there. So we need to properly identify the corresponding switching state. So that will be time consuming, and also it requires lot of computation and lot of optimization techniques we need to use to select the appropriate space vector for a particular voltage generation, right? So that is for three phase. The formula is simple. So the how many switching states, so that is equal to the number of phases to the power of number of levels in the phase voltage. For example, it's a 5 phase, so it is 5 phase 5 level inverter, so it is 5 to the power of 5, so is the answer for the number of switching states. So out of that, the 0 switching states will be equal to the number of levels, right? So here those are the difficulties, especially we have the space vector modulation techniques. So therefore most of the times we move to the carrier based techniques. So common these carrier based techniques are this multi-carrier PWM techniques. So these are the natural extension of the whatever the methods that we have for the two level inverters. So these are the natural extension of that one. So there are two methods are there. So in that one is the level shift PWM technique and the phase shift PWM technique, right? So another methods are there like hybrid PWM techniques or hybrid modulation. So in this hybrid modulation, so this is used for the asymmetrical DC sources in the cascade edge bridge inverter. So next one is the selective harmonic elimination. So this is very familiar technique for the low speed motor drives. So selective harmonic elimination. So same methods. So we can also extend it for the multi-level inverter. So the next one is the nearest level control. So this one especially used for extremely high levels when the levels are exceeding 20, 50 or somewhere around, right, 100 levels. So in that case the nearest level control algorithm, so which is very popular techniques. So that is used in the applications where you have the number of levels are very high, right? So today we will discuss about this commonly used carrier based techniques. One is the level shift and the phase shift algorithm. So first I will describe these methods. They are simple methods only. It's just the implementation is straightforward. And next we'll see how to simulate these things in the MATLAB. Right. So as we discussed, so there are two methods are there. So one is the level shift and the phase shift PWM technique. In case of level shift, there are three more alternatives are there. So these are just for the carrier arrangements. So that's it. So first thing we'll start with the phase shift PWM technique. So first we'll start with the phase shifted multi-carrier PWM technique. Right. So here right. So if you see right. So if you see this cascade H bridge, right? So here as we discussed, each phase we need to control separately, right? So that means A phase we have separate modulating signal and the carrier signal, B phase, C phase, right? So first A phase, so how many switches are there? If you observe that there are 4 switches, so 8 switches, right? In each H bridge we have 4, so that means you have 8 switches are there in A phase, right? So in A phase you have 8 switches are there, right? So these are the 8 switches. This is 4 here and another 4 here. Alright. So you know that, right? So in sine PWM technique, so if it is one switch is above, we'll compare the carrier signal and the modulating signal. So one is above the carrier signal, so we'll turn on the switch, and that bottom one will be turned off, right? So this is how the complementary implemented, right? So according to that, so to control these 8, right? So how many carrier and the modulating signals we need to compare? So you require 4, right? So 4 carrier signals is required, but you obviously have one modulating signal. So modulating signal is responsible for the output voltage and frequency generation, right? So that you can't duplicate one. So therefore you require 4 carriers, right? So 8 switches are there, 4 carriers are there. So each carrier will interact with the modulating signal, and it will generate the firing signal for the 2 complementary pair, right? So it will generate the firing signal for 2 complementary pair, right? So therefore, so for anything, right? So for any that means if you summarize in that, right? So for M level inverter, so usually we require M-1 triangle carriers. For M level inverter, we require M-1 triangle carrier. This is a 5 level inverter, so therefore you require 4 triangle carriers. Right. So depending on this carrier arrangement, so we have 2 methods are there. So one is the level shift PWM and the phase shift PWM. Alright. So in case of phase shift PWM, the idea is simple. As we discussed, we have 4 carriers are there. All the carriers are of same frequency. All the carriers are same frequency, and all will vary from +1 to -1. Right. So all will be vary from +1 to -1. So if you want some output voltage, so we will normalize that output voltage. Right? For example, for inverter, if you want some 400 volts, so we will normalize the output voltage. Generally, normalization can be done by dividing the output voltage with the required output voltage with DC link voltage or half of the DC link voltage. So that is how we will convert into per units. Right. So that means you have 4 carriers are required. So each carrier of same frequency, and all carriers are ranging from +1 to -1, right? But here we will maintain a phase shift between the individual carriers, so that phase shift is calculated by 360 degrees by M-1. So meaning is that, so in case of 5 level, so we have phase shift of 90 degrees, right? So that means first carrier after 90 degrees of the carrier period, so we have another carrier will start. Understood? Clear? So this is the carrier arrangement. So for 5 level case, so you can see that, right? So carrier are arranged something like that. So we have one carrier. So if you see the first carrier, which is changing from -1, with the starting point of the first carrier is -1. For the second carrier is 0. For the third carrier, so that is +1. and the fourth carrier which is 0, right? If you see all together in one single scope, so there will be some shift in the carriers, all right? So now if you see that the first carrier and the modulating signal, so both are interacting each other, and a firing pulse, so which is generated here. A firing pulse is generated here, all right? Similarly, so that negative pulse is not shown, that inverted pulse is not shown for simplicity. Similarly, this carrier is interacting here and it is generating a firing pulse for one device. And this is also interacting here, it is generating a firing pulse. Alright. So here we are showing only 4 firing sequences, but the other 4 can be generated by simply connecting a NOT gate. Understood? So now the point is that we generated 8 firing sequences. So now how to give to the individual devices, right? So let us assume that we have switches, something they are arranged something like that, S1, right? So this is switch S2 and this is S3 and S4. In the bridge, top bridge, we have 4 switches, right? And named like this. Similarly, we have on the bottom side it is S5, S6 and this is S7 and S8. You can imagine, right? So S1, S2, these 4, S1 to S4 on the top H bridge and S5 to S8 are on the bottom H bridge, right? So now we have, so these two are complementary, right? And similarly these two are complementary, these two are complementary, these two are complementary pairs. Understood? So now you compare the first one. So first one, so whatever you obtain from here, right? So this one will directly go to the S1 switch. Alright, so complementary of this one, so which is go to the S2 switch. Understood? Similarly, the second one, so here you have to follow the U pattern, right? So therefore, the second one, so this one will go to the switch S5, and the complementary will go to the S6. Understood? Similar to third carrier, so which is again shifted by another 90 degrees from the second carrier. So we need to follow like this S8, right? S8, and the complementary will be S7. Understood? Similarly, this one, so this is S4, right? S4, and the complementary will be S3. It's clear? So that means you need to follow a shape something like this. U shape. It's clear? So here by doing so, so each one is, you know that, right? If it is H bridge, there are 2 modulating techniques, right? One is the unipolar PWM and the bipolar PWM. So by doing so, so here all the H bridges individually will be operate in a unipolar PWM method, right? Each H bridges will operate in a individual or unipolar PWM techniques. I will show you, right? So this is the output. For example, this is for 7 level. So we used 6 carriers here, right? So we used 6 carriers here. So that means the pattern will be something like this, right? The pattern will be something like this. And if you observe that, so this is the one, right? So this one is the first H bridge output voltage. You can see this one, right? This is your unipolar output voltage. You have both positive off cycle and the 0, and as well as negative off cycle. You can see this, right? So VH1, so both it is operating itself a unipolar PWM technique. Understood? Similarly, so VH2, so that is also operating in unipolar PWM mode, and VH3, so that is also unipolar PWM thing. But if you combine all the things like VH1 plus VH2 plus VH3, see what you got? So that is the phase voltage, right? So that will be the phase voltage. Understood? This clear? And if you see, observe, another interesting thing is that, right? So all the pulses are same only, right? So because we carrier signal is same, modulating signal is same, all the pulses are same only. If you see here, in this one, right? All the pulses are, yes, starting from switches S1, all pulses are same. All are of same frequency, right? But they are shifted only. right? Just they are shifting only, right? So nothing we done. Just first pulse and second pulse, so they may be shifted by 90 degrees, second and third shifted by 90 degrees, third and fourth shifted by 90 degrees. That's all. Right? So by doing this, all are operating in the unipolar PW mode and you got the output voltage, phase voltage. Right? Understood? So same thing we need to employ for the B phase and as well as C phase. Understood? So this is how to operate for a cascade H bridge, right? So in case of like flying capacitor multi-level inverter, as we discussed, we have switches or something like that: S1, S2, S3, S4. All right. So we have S1, S4 dash, S3 dash, S2 dash, and S1 dash. So these are the switches in a flying capacitor multi-level. And another thing is that, so this method is not applicable for the diode clamp multi-level inverter, because in diode clamp there is no switching redundancy, right? So if you want one voltage level, you have only one voltage path. So in that case it is not applicable. So this is in case of flying capacitor, you can see that, right? So this one will controlled by one carrier. So this is controlled by another carrier. This is controlled by third carrier. Right. So this is controlled by the fourth carrier. Simple. So whichever is complementary, so S1 and S1 dash, the extreme ones, so you require one carrier. Similarly, S2 to S2 dash, you require one carrier. So S3, S3 dash, you require one carrier. Likewise, right? You can imagine the diagram, right? I will show you quickly. So this is the one, right? We have four switches are there, right? So this is how you give the firing pulses in case of a flying capacitor multi-level inverter. So as we discussed, so this is not applicable for the diode clamp. So why it is not applicable for diode clamped means, so there is one drawback with the diode clamped is that switching redundancy, right? So the major drawback is if you want one particular level, right, you have only one path, right? So you have only one path for one voltage level. So alternative paths are not there. If alternative paths are not there, right? So and another thing is that if you see that, right? So if you want some E level, this should be on and this should be on. So this should be off for the, if you want positive DC voltage, right? If you want negative DC voltage, so this should be on, so this should be on, this is off and this is off. Alright, so that is for the negative DC voltage. But if you want only the some zero voltage, right, this should be off and this should be on. Right? Understood? That means the switching pattern is not same. The inner switches are conducting more period of time compared to the outer switches. So that means if this switch, for example, if you see that, right, if you require positive E voltage, you need to turn on this switch. If you require 0 voltage, you need to turn on this switch. Right. So whereas this switch, the stop switch, so this is only need to turn on, so whenever you require the maximum positive voltage. Similarly this one, if whenever you require the maximum positive voltage, so then only you need to turn on. Understood? So therefore the switching redundancy is not there, and this all switches are not conducting same, right? All are not conducting at the same frequency, but whereas in the phase shift PWM, that what we discussed, all switches are supposed to conduct same period, right? The pulses are same, just we have a phase shift, right? So therefore this method is not applicable. This you understood, right? So next we move to the other one. So this is level shifted PWM technique. So this is just straightforward. So same thing. So we have m number of levels are there. So m minus 1 number of carriers are there. So but instead of these things, right? So these carriers are vertically disposed, right? So this is how these carriers are arranged. You can imagine, right? So earlier, so all are having the same magnitude, so which is vary from +1 to -1. So whereas now it is vary from the first one, that means the +1 to -1 region is there, right? So that is divided into the different carry. 4 are there, right? So this is the arrangement 1, 2, 3, 4. So this is the arrangement for the 4 carriers. Understood? If it is 3 are there or if it is 6 are there, so the arrangement may be slightly different. Right. So first carrier, if you see that the green one, so which is changing from the 1 to 0.5. So the second one which is changing from the 0.5 to 0, and third one changing from 0 to -0.5, and the last one is changing from the -0.5 to -1. Understood? So here also everything is same. So same thing, right? For example, interaction of the first carrier with the modulating signal. So it is generate the switches for the S1 and the S2. See the same diagram, right? So interacting the first one, first carrier, the green one, so that will generate S1, S2. So next S5, S6, next S8, S7, and S4, S3. So no need to change anything, right? So the same pattern will follow. Same thing for the diode clamp, everything, right? For example, if you consider diode clamp, for example, diode clamp, we have S1, S2, S3, S4, but it is S1 dash here, S2 dash, S3 dash, and S4 dash. See that diode clamp. This method works for the diode clamp. So this S1 and S2. So one carrier interaction. So this is second carrier interaction, third carrier, and this is the fourth carrier. This clear? Right. So these are straightforward. Once you carrier arrangement, so no need to change the firing sequence. Just change the carriers. That's all. So you'll get the output voltage. Understood? So normally when to take ramp and when to take, there are two things. One is the single edged and the double edged signals, right? So ramp signal is usually for the DC. So whenever if you want to reduce the ripples in the output voltage, so generally ramp signal is preferred. That is single edged one, right? If you want to reduce the harmonics, like you need to use the double edged one, so like the triangle carrier. So that means if the output voltage you are supposed to control is the DC, the ramp waveform is preferred. In case of AC, you are supposed to use the triangle carrier. That is the basic things. Yeah.
So this waveform is for how many levels?
This is for 5 level.
5 level.
Yeah.
So if I say that my modulation index is less than 0.5,
It will cut down
it
levels.
will cut on,
Yeah.
it will work as in 3 level.
Yeah.
And if there is a less than 0.25, it will work as 2 level
2
inverter.
level.
So we can use different type of inverter by using adjusting the modulation index.
Yeah. If it is same thing, right? If it is one modulating, it is beyond that, right? So that means one bridge itself is not producing any power. Okay. So that means if you see this one, so here, see these two are together controlling the top bridge, right? And these two are together controlling the second bridge, bottom bridge, right? So that means if the modulating signal is less than 0.5, the bridge itself is not producing any power, right? That is simply a 3-level inverter. That's all.
I do have 3 level inverter, but I'm talking about 3 level inverter.
Hmm.
I have 3 level MPC inverter and I have to work in as a 2 level inverter. So I have to fix the modulation index less than 0.5.
Yeah.
So it will, I'm talking about hardware. It will work as 2 level inverter. Some
Yeah, it will work as just 3-level inverter only. You will get 3 level, not 2 level. You will get 3 levels. So that is the drawback with the low speed. So for example, if a low speed operation is there, right? So here the output voltage itself is reduced. So that means the number of levels are reduced. So that's why normally if you are, most of the times we will operate at the, for example, in case of electric vehicles, that problem is there. So we have some variable speed, low speed operation and to high speed operation, we have continuous change. But in case of industry, normally that much variation in the speed will not be there, right? So like most of the times we have constant speed operation or some drooping is very less only. So based on the voltage, whatever you record, you will adjust that, right? Okay. But the thing is that, so when the operating with lower modulation index, it will cut down the levels, right? So in case of level shifted converter, so enter one H bridge, the output voltage will be 0. So whereas here, Here the thing is that in case of phase shift PWM, so one output is not 0, so whatever these pulses are there, right, so this output voltage will be reduced.
I have one module of 3-level MPC inverter. I have to check it as a two. I have to work it as a 2-level inverter.
Hmm.
So what else I need to do? Because there's a module, fixed module made by one company. This is 3-level inverter, MPC
Yeah,
inverter. I want to work it work that inverter as a 2-level inverter.
just reduce the modulation index less than 0.5.
0.5.
That's it work.
It will same work as a 2-level inverter.
Yeah,
Okay, sir, I'll give
same output you will get, same. Only the outer switches will not conduct, only the inner switches will conduct.
same as 0.5. मतलब we are keeping switch number 2 and 1 and 2. We are keeping it as an always on, and we are just triggering top and bottom, the topmost and the bottommost. We are just triggering that
No,
will
no, the top and bottom will never trigger, right? They will not trigger.
if we have the positive sequence, then we have to switch
No, no, that will not make any interaction, right? The switches will always 0.
if this is always zero. How can we get positive voltage,
Hmm.
negative voltage?
How to?
How we get positive voltage and negative voltage if their switches are always on?
So this one is there, right? So if it is not there, that it is not making any interaction, right? The switch will be either continuously on or the continuously off only.
If we get the if we want the output, we have to be continuously on. Switch number 2 and switch number 3. We
We have other two more switches are there, right? So that will control the. That will control.
triggering top and bottom. We are toggling it as per our desire.
Hmm. So that will be controlled, right? So whereas 8 switches are there, out of 8 switches, so 2 switches will be continuously on and continuously off, right? So remaining switches will be there, that will work, right? Right. So another thing is that, so these are the firing pulses produced by the level shift PWM. If you see that the pulses are not same, right? All are not of same frequency. For example, this is making 1, 2, 3, 4, 6 intersections or 6 pulses. So whereas this is 1, 2, 3 pulses only. So this is 1, 2, 3, and this is also 6 pulses. So all are not operating at the same frequency, right? But if you add all these pulses together, right? So we will get a of something like, MF, right? What is MF? FCR by FM, right? Modulating signal frequency. If we add all these pulses for all, so you will get, for example, in this case is MF is 20, right? So roughly you will get 20 here. So this is 6, 4, 4, maybe it is 6, roughly you will get 19 or 20. Understood. Some narrow pulses will be there, so that may not be observed, but theoretically you are supposed to get 20 if we add all the pulses together, right? So there are two things we need to define here. So one is the, or any inverter, we need to see its harmonic performance, right? Any inverter we need to see its harmonic performance. So for that, if you see the harmonic performance here, so this is the output produced by the phase shift PWM technique. So this is the output phase produced by the phase shift PWM technique for the 5-level phase. This one is the phase voltage, and the top one is the line voltage, right? And its corresponding THD is around 29.76. And we see this for harmonics or harmonic spectrum. So harmonics are centered around the carrier frequency, some multiplied by carrier frequency 120, right? So now this is important thing. So why exactly it is 120, right? See here, the first thing is that, so this is FCR is 1500 H, right? What is MF here? What is MF? What is MF here? What is MF? 50 H it is 30, right? So this is 30, right? You might know that, right? Unipolar or bipolar, so how it is shifted, so that all depends on the MF under the linear range, right? So for example, and here there are two things we need to remember. One is the switch frequency, at what frequency the switch is operating, and what frequency or the effective frequency of the inverter. So you know that if you study the unipolar PWM method, the inverter frequency is twice the bipolar PWM technique, right? That's why the harmonics are appeared at the 2 MF frequency, 4 MF, 6 MF frequency, right? If you remember that, same thing here. So in case of level shift or the phase shift PWM technique, so in case of phase shift PWM technique, all the switches are operating at the same frequency, right? So therefore, the effective frequency, that means all switches are on and off equal to the carrier frequency, right? So therefore, the effective frequency, so which is equal to m minus 1 into FCR. So this is the inverter frequency. So meaning is that, so in case of 5-level inverter, so m minus 1, that is 4. In case of our case, our MF is 30, so that means 4 into 30, 120. So based on that, you have sideband harmonics, so which are appeared at this cluster 120, 120, 240, it will be appeared. Understood? Clear? Same thing, right? In case of in case of level shift PWM technique, so this is slightly different. All are not operating at same frequency rate. All together are operating at the MF frequency. So therefore, here the inverter effective frequency is which is equal to the carrier frequency. Inverter effective frequency, so which is equal to the carrier frequency. So in case of level shift PWM, so both carrier frequency and inverter frequency both are same. In case of phase shift PWM, so it is m minus 1 into MF, or m minus 1 into FCR. Understood? These are all under the linear if the MA is less than 1. Right. So now how we compare with the level shift PWM technique. See here this one, so it is a period at 30 only. Okay, so these are a period at 30 only. But the thing is that if you compare the THD is just 17.58, so when compared to the phase shift PWM technique, and the waveform are much closer to a sine waveform. You can see that the waveforms are much more cleaner in case of level shift PWM technique. Understood? So why? Because if you observe the changes here, this extra thing is there, right? So this one, and if you see this one, right, this is clean waveforms. That middle portion is completely absent. All right. And another thing is that you can also see that the higher switching is operating because we have thick lines are there, right? So a lot of switching toggling is there, right? So we have higher frequency operation. So here also lower frequency operation because the inverter frequency itself is less. And the good thing is that, so the level shift PWM produces the better waveforms, right? In fact, the best waveform it will produce. So this method you cannot, we cannot beat this. Whatever the output waveform that obtained by the level shift PWM. This is the benchmark one. You cannot even beat this one, right? That means you cannot make it better one. So that will gives you the clean output voltage. So when you have the modulation index is at unity or near unity, right? So any method you are using like SVM or anything, right? You cannot make the output, or this one is benchmark. We will every time we will compare with this method only, right? Whether it's new technique is there or anything, right? So we'll always compare with this method. Right. So you can see that, right, the levels are simply changed, right? You can see that there is no extra things, no extra switching, nothing is there. It is slowly, each step is incrementally increasing, right? But the drawback with the level shift PWM is that, so all devices are not operating at the same frequency, right? So therefore, if the modulation index is less, some of the edge bridges are continuously off. They're not at all delivering any power. All switches are operating at the different frequencies, right? So therefore, if you compare the some characteristics or something like that, so here the device switching frequency is same for all. So whereas this is different, and the conduction periods are same here. So this is different, and the line-to-line THD is good here, but we'll get the best performance here. But the inverter topologies, so this one is applicable for the flying capacitor cascade edge bridge. So whereas this one, this level shift PWM is applicable for any any inverter topologies, right? So most of the nowadays we have some other topologies like T-type or some other topologies are there. So for almost all any PWM any inverter, so we can directly apply so this one, right? And capacitor balance or the sharing, power sharing, right? So here the power sharing, if the switch frequencies are same, all H bridges are delivering equal power, all switches are same equal, right? So naturally we can balance the capacitors, right? So therefore, so with this method we can naturally balance the capacitors. So whereas this one it is difficult. right? So this one is difficult, so we need to adopt some other methods, right? We need to adopt, if you are using, still you are using a level shift PWM, so you need to use some other methods to adopt the, or to get the equal performance or equal power sharing among the H bridges or something, right? Right. The method is such way that, right, so all are equally shared, right? Okay, whatever it is shared in the bands wise, right? We have one band is there for particular level, so obviously the output voltage will be, you will get a stepped waveform, right? You will not get the intermediate waveforms or intermediate switching. So there are some methods are there, same LS level shift PWM technique. So we can still transpose the carriers. Let us assume that this is a carrier transposition. If you see that there are different levels are there, right? So this is for different cycles, 4 cycles or 5 cycles here. In first cycles, if you see what is the change you observe, the carrier is changing its position, right? Earlier it is one position, now it is changed to two, and the next sequence it is changed to 4 5, and at the fifth cycle again it's come to the first position, right? So that means this is now you are just shifting the operation, right? At your one cycle you are giving the merit to the one H bridge, and the next cycle you are giving merit to the other H bridge, so that over 4 cycles or 5 cycles, so you will get the uniform power. So this is one way. And another way is just within one cycle, one carrier period or one modulating period, you can get the same thing, right? So just instead of changing it over one might, the green one, see, right? So this green one carrier, it is changing its positions. So these methods are known as the carrier rotation methods, which are very popular, especially for this. We can use the level shift PWM technique, and also at the same time, see here also you can see that all are operating at the same frequencies, right? All are operating at the same frequency. Still, you will get the output voltage, which is equal to the level shift PWM technique, right? Just we need to change that, right? So after end of the carriers we need to change the positions only. We'll store these values in the simulation, right? So after that you need to add some offset. If you add one, for example this one, if you want to raise this one, right, you need to add one offset, 1 2 3, like some step waveform you'll generate, you'll add offset for that. For example this one, this is the one is there, right? If you want to bring this one, you need to subtract one offset value, right? Some minus -0.5 or something. If you subtract, you will get this. If you want to raise this waveform to here, you will add one more one offset, right? Some 0.5 if you add, right, you will get them. At what point means you need to add some offset, something like this, you will get the waveform, right? This simple only. Hmm. This thing, this that effect will be overcome here. So now all bridges will operate same. Okay. So now earlier we have individual that can be overcome here, right? So now all are operating at the same power levels. Understood? So I made some simulations. I will quickly show, and also I will share these. You have DC sources on one end, right? So what kind of inverter this is? Cascade H bridge, right? Okay. But as long as told you, right, as long as you have a DC sources on this side, right, it is fairly simple, very straightforward. So it's very simple, right? But the real problem or the real challenge will come. So when you have a connected to the AC source and you have the capacitors, right? Or else when you connect some batteries or some PV, if you are integrating or controlling the active and reactive power, that will be the real challenge, right? So I constructed one cascade edge bridge of how many levels this is? 5 level, right? So 5 level cascade edge bridge, so we have right now, right? And I can see, so I generated 3 modulating signals, visible. Okay. So from this, what kind of PWM technique this is? or else I will open this dialog box. So here, so 1.5 1, right, and this one 1.5 0 0.5 level shift PWM technique, right? I just carriers on the other side, that's all, right? And here I have one trying means sinusoidal supply here, some with some modulation index, some MA, a defined MA at the right. And if you see that, right, so one phase is visible, right? Okay, it's clear. So how the firing signals are given, you can see, right? So triangle, each phase or carrier 1, and comparing with that, so accordingly I generated the switches, right? Accordingly I generated the what we say firing pulses, and I given to the individual devices like U shape, that is remains same only, right? So here you can see this, right? So this is A phase. Similarly, you got to give it for the B phase and the C phase, right? And another thing, if you have more number of switches are there, so you have to give a proper naming, right? So not give a some random like 1 2 3, right? It will be always difficult. So if it is a bigger circuit, so many circuits are there, so you have to give some proper naming. For example, so here A phase S11 1 2 1 bridge, first bridge, second bridge, or A phase B phase, so that you need to know, right? The same thing it is there for the B phase C phase, right? B phase C phase as well. The only thing is that the modulating signal is shifted by 120 degrees and further shifted by 120 degrees for the C phase. Alright. So we will run this one, and also I just for simplicity I connected some RL load. This is just an open loop one, right? I connected a RL load here. I will run this. Running. Yeah, it's running. And I am measuring the phase voltage and the line voltage. So this one is the phase voltage. You can see that, right? So phase voltage consists of some levels here. So how many levels we have? 5 levels, right? So 5 levels inverter output you are getting, right? So now we'll close it, and I will open the this one. So this is line voltage, right? You can see the cleaner waveforms, right? Right. So you can see the lower switching and the cleaner waveforms. Understood? So you can also see its harmonic performance, something like this. Yeah. So you know how to see the harmonic performance, right? You might be familiar with that. So we need to store these things in the workspace, right? After that, this is the red one is the highlighted one. So here maybe the start time, we may slightly change the start time just to avoid the, I will just slightly change the start time, right? Okay. So next one, in number of cycles, maybe you can prefer somewhere between 1 or 2 cycles. Generally somewhere between 3 to 10 is preferred. I think we don't have that many cycles I simulated. Just putting here. Okay. So why it is like this? Okay. So frequency is 50 Hz we considered, right? So 50 Hz is a frequency, and I will add one more zero here. Okay, I will change it to harmonic order. This is fine. I think this is giving something else waveform, right? And there is another waveform. This is not the one. There is another one is stored already stored in the this one. I don't know. Right, you can see here, right? The carrier frequency I selected as. I think I don't know. You can select, right? You are getting somewhere around the 60, right? So harmonics are centered around somewhere around 60. I think I will slightly increase it. You can see here, right? The harmonics are centered at what frequency? 40, right? 40, 80, and 120. Something like that is shifted, right? So why it is? I think if you see here, how much carrier frequency I selected. So FCR 2000, right? If you see here, FCR is 2000, right? So 2000 divided by 50, so that is corresponding to the 40, right? So therefore you have harmonics which are centered around the 40, similarly 80, 120, and 160 somewhere, right? I think in the phase you maybe you will get the better waveforms, right? This you understood, right? We will. So next one, you can also, as we discussed, right? What happens when you reduce the modulation index by something? Okay, we will reduce the modulation index as we discussed. We will make it point 0.4, right? So we'll make it point 0.4, and we'll see what happens. See here, right? It is as good as a two-level inverter, right? Similarly, the line voltage is also reduced, right? Line voltage, it's 5-level inverter, right? It will work. It will work. Hmm. It will work, I think. That is basic property, right? You're not firing any, giving any pulses, right? That means it will be zero only. You are using 3-level. Okay, we have diode clamped. Hmm. We need to monitor the capacitors, right? Now you have DC sources, you're not worrying about, right? So if the capacitors are not balanced, all the voltage levels are not same, right? You will not get the clean waveforms. The voltage waveforms will change. One height will be 90 volts, another will be 92 volts, 93 volts, 89 volts. You will not get a cleaner waveforms. That is fine. That is fine. Closed loop, we need to control the real and reactive powers both, right? That is difficult part. Okay. Not only for any multi-level inverter, basic thing is that multi-level inverter, especially operating closed loop, is a tough, slightly challenging thing, right? That is general statement, right? So we have capacitors are there. We need to balance the capacitors. Sometimes the capacitor balance will be difficult, especially when it is drawing the real power, right? Motor, in case of reactive power also, all the phases, the load may be balanced or some unbalance will be there, and the sources will be distorted. All will impact the capacitor voltages, right? Any deviation in the kpk parameters or some deviation, any deviation will be there. So that will, first thing it will impact is the capacitors, right? If capacitors are deviated, so automatically all the voltage will be deviated and it will cascaded.
So what your suggestion if you want to control, then SWM is okay or SVM is okay for good for multi-level inverter?
Anything, right? SVM is maybe up to five level, it's fine, right? Beyond that we have to use this method or the nearest level control only, right? So maybe 5 levels also you will get, I think 3 to the power of 125 switching states you will get for 5 level case only, right? If it is beyond that you will get more and more, right? It is not that easy to select a particular state. So lot of optimizations you need to do, lot of calculations you need to do, and some methods like the model predictive control or some optimization techniques you need to involve, right?
So can you suggest about virtual voltage vector?
Hmm?
Can you comment something on virtual voltage vector? Because this convert a virtual voltage vector in SVM is also there. Quantum virtual voltage vectors.
And so those are the methods, no? Virtual voltage we will inject some or we will I think in virtual, as if I remember,
We are injecting
we
some
are injecting or some vectors, right? So whenever we have some redundancy is not there, in that case we will inject some vectors or we assume some vectors are injected. So based on that we will do the calculations, okay? This is for the 3 level diode clamped case, right? 3 level diode clamped case. We'll also quickly see this one. So this is straightforward, right? Okay, straightforward. So as you can see, this is also a level shift PWM technique. So that is the only options you have, right? And also you can see its control here, right? So we have just 4 switches are there, one, two, complementary of one. So this is complementary of this one. So this is complementary of this, and this is complementary of this. Then this switch and this switch. Understood, right? And another thing is that I will also run this one quickly. So you are getting 5 levels, right, in the line voltage. So you are getting 5 levels in the line voltage. Maybe I think I don't know whether you are getting 5 levels in the line voltage, right? And also we will change the modulation index like we did earlier, right? You hardware also it's supposed to work. Okay. Sometimes what happens is that, right, if you are using some modules or something, right, the continuous operation of the switches will not allow. Hmm. Simulation for if you want, that depends on sampling time what you took. Right, if the sampling time is not good, you will not get the perfect ones, especially at the zero, at the peak level you may not get, right? Okay, so there is something like that. The generally the carrier frequency and the sampling time both must be integer related, right? The difference should be integers, right? Yeah, for three phase, I think there are two things. It should be divisible by three, and it should be some integer multiple, maybe 30 times more than that or something like that. They will take. Hmm. sampling frequencies. Okay. Sampling that should be in the micros, right? Maybe somewhere between 50 or normally somewhere something less than 50 in 50 microsecond, that range you are supposed to keep. Okay. If it is less than that, it will not work. Okay. So it's supposed to be in the micros. Mostly, if it is switching frequency too much, like 100 kilohertz, at least you should take at least 1 second or less than that, right? So you need to check whether you are making some proper carriers or not. If the carriers are changing properly or not, that you are supposed to check. So and accordingly, you need to reduce or increase. You need to reduce the sampling time. The biggest difficulty in the hardware is that, especially in if you are using some platforms like DSpace or FPGA, only thing is that sampling time, right? So all your simulation are supposed to be done within that period, otherwise it will throw some overrun exception or over burden exception within that time, right? We have to make sure that, and at least for real time operation, all the things is supposed to be finished within 50 microsecond. That is the best thing, right? We'll also quickly see the your time. I think phase shift. I think one is there on phase shift. Where is that? Yeah, this one. Yeah, diodes by switch, and we need to operate that switches based on which capacitors is there, right? So you need to trigger that particular one. You cannot randomly trigger based on the capacitor voltages. So you need to identify, so which one, if you supposed to turn on, the capacitor voltage will be recovered. So that hmm? The basic is LS. This the basic structure is same only. For the remaining two structure, two devices extra will be there, right? That thing you need to use some extra controller, right? Basic is same only, right? For even for the in one class we discussed the additional switches, a two quadrant chopper we are connecting, right? That will not impact the this operation. Both are different, right? Maybe the some no what I said, there is some nowadays drivers are not allowed to continuously on. Okay, or in PWM also something will be there. Hmm. The problems might be maybe driver circuit. Some drivers will not allow continuous on for a particular switch, right? If it is continuously on, it will be completely shut down. So you need to check whether the voltage across each device, whether it is working or not. That is just debugging is simple only, right? You just check the firing pulse whether it is going or not. Simulation, what is the firing pulse is there. The same thing is there in the hardware you are getting, or that's all you need to check. You keep simulation one side, you check the firing pulse, at the same time what is exactly happening there, you just check it. Okay. This is phase shift PWM. I think just now I run same thing. I just connected some transport delay here. I just connected some transport delay block here, right? I not changed anything, right? Power circuit is remain same. This other firing circuits only same. Only thing I changed is this carriers arrangement, right? The first one and second one, they are slightly shift is there. The shift which is 1 by FCR, that is the period. So from that 90 degrees, right? 1 by 4 into FCR, that gives you the 90 degrees of the carrier period, right? So if you are doing so that becomes a phase shift PWM technique, right? And if you see the phase voltages, they're like this. I think the modulation index we are not changed. You're getting the waveforms, right? And also you can see the uh, see here this extra switchings also you can see here, right? Also we can see that harmonic performance. Quickly we'll see. So here carrier frequency I selected 2000, right? So 2000 divided by 50, that is 30. 30 into 4 you are supposed to get at 120, right? And we'll see whether you are getting that or not. You're getting, right? So that is roughly, if you see in the order, roughly it is, why it is 160? Okay, I kept 2000, right? So 2000 means 40 into 4, 16, 160, right? Understood. Clear? I will stop here. I will forward these files to you. You can break down for your analysis, right? You have any more questions? You have any questions?